It's Math and Beats, and it is another video. We are going to follow up on the previous discussion in which we looked at applying derivatives to position functions, in which instead we look at a few more examples in which we apply derivatives to other portions of the real world and interpreting derivatives as rates of change. Let's go. All right, first thing we're going to do is discuss an economics situation in which we look at average and marginal cost, as we're going to see. So given some cost function down here, as we say, let's just call it C of x here. Let's say this cost function gives, hence the cost, in producing the first, say, x items, whatever they might be, in some type of manufacturing process. So there's some company, they're producing some amount of things, x numbers of things, whatever they might be, these items, and C of x tells us how much that cost. Cost function. Cost depending on x. Then we can also talk about something which is called average cost. And so we'll denote this by C bar of x. The bar, of course, familiar with denoting the concept of average. And so we say that the average cost here, C bar of x, to produce those same x numbers of items is just C of x divided by x. So you take your cost function in producing x items and you divide it by the number of items, an average. Average cost. And then finally, there's what's called marginal cost. And here's where our concept of a derivative starts to take place. The marginal cost function, right here, C prime of x, so that's the derivative of the cost function with respect to x. If you prefer, you can write that as dc dx. And now, this doesn't give us exactly what we're after here, but it does give us an approximate cost of producing one additional item. I forgot the right item. Item after producing, all right, we're right here, after producing x items. So in other words, I produce x items, I got my cost function, C of x. Tells me how much that costs. I can also tell you that the average cost of producing those items was, well, the average cost we saw above. And now this marginal cost function, which we're claiming C prime of x, this is trying to say I'm going to use the derivative to predict an approximate cost of producing one more. So like one more than x, right? X plus 1, if you will. I want to draw a real quick graph here to conceptualize what that means. Eventually, later in this discussion of calculus, we will focus on estimations using derivatives. But for now, let's just say I have some cost function, whatever it might be. Maybe my cost function looks like that. The green graph there is y is C of x, my cost function. And then we'll just go and pick a location. Let's just say right there, that's x. Then, of course, its output is C of x. So that's the cost of producing the x items. Now, what we're saying here, we're going to produce one additional item, right? So that just means I go wherever that is. Let's just say right there. And that's x plus 1. So that the distance between those two different x items is 1 unit. So one more unit, right? Where am I? I'm right there. And that output, of course, is C of x plus 1 here. And so you notice that over this interval, we could think of that length, that's delta x, which of course is just 1 here. But then right there, that amount of space is C of x plus 1 minus C of x. And you say, okay, well, I could do my thing like we were doing in many previous situations and draw the secant line that goes through both of those. That secant line slope, right? The slope of the secant line there is going to be equal to, well, C of x plus 1 minus C of x, the change in output, over delta x, but that's just equal to 1, right? So really it's just C of x plus 1 minus C of x. And so we can see the change, right, from c of x to c of x plus 1. What is that change? That change is actually the same as the slope of the secant line in that particular instant. And what we'll do is instead we'll draw the derivative at x, right, c prime of x. And if I draw a tangent line there, like so, then we can see that indeed the slope of the tangent line of c, so of course this tangent line here has slope c prime of x, and so since the slope of the secant line is telling us this change, well, the slope of the tangent line is approximately equal to that same thing. And so that's why we say, okay, if I use the rate of change of the cost at x, that is a good approximation, because we're only 1 unit away from x, to coming up with how much it would cost to produce one additional item after x. So as we can see, we're using the derivative here in a situation in economics that we can. So that's what's so great. Derivatives can be used in so many situations, and this is just that first example in this video. So let's do an example now using this stuff that we just talked about. Suppose that we have this situation here, and that is we have that the cost of producing X items somewhere, some company producing some things, is given by this cost function right here. C of x is negative 0.1x squared plus 25x plus 125. And let's just say that's true for producing between 0 items and 1,500 items. And we're going to assume here that C is measured in hundreds of dollars. So not dollars, so units important here. First thing we want to do is just come up with the average and marginal cost functions for C of x. Well, of course, the average cost is going to be equal to C bar of x, as we saw above, which is just C of x divided by x, right? Take the cost of producing x items and divide it by the number of items. So what do we get? Negative 0.1x squared plus 25x plus a 125, that's my numerator. All of that divided by x, so what do we get? We'll just take each term in the numerator and remove a factor of x, and we get negative 0.1x plus 25 plus a 125 x to the negative 1. So, of course, that last term, 125 divided by x, is the same as 125 x to the negative 1. So there's my average cost function for this particular situation. How about my marginal cost? So let's go ahead and pick that up. Marginal cost function here is going to be equal to, well, remember that's just C prime of x. So if I differentiate my cost function above, power rule, power rule, power rule, I get negative 0.2x plus 25. So there's my marginal cost function. So we found them. Now we should do stuff with them, right? Now we're asked to find the average cost and the marginal cost for the first 100 items that are produced here, and then think about interpreting what that really means in this situation. So let's start with the average cost. So average cost is going to be C bar of 100, right? Just that's my X here is 100 items. So plug that in, I get negative 0.1 times 100 plus 25 plus 125 times 100 to the negative 1, or 125 divided by 100. And if you press some buttons, what you're going to get at this gives us a 16.25. Okay. Now remember, we're going to interpret that in a minute, keeping in mind that this cost function has units of hundreds of dollars. Okay, so we found it now, but we'll interpret it in a moment. And so let's go ahead and find our marginal cost, C prime of 100. And if you plug in 100 into the marginal cost function, you get negative 0.2 times 100 plus 25, which is going to be equal to, press more buttons, it equals 5. Okay. So we found them, right? We determined the average cost and the marginal cost for producing the first 100 items. However, it's not just all about, oh, we found these numbers, right? What does it mean? What does it mean here? So let's talk about what it means. Well, let me just draw a little line here. C bar of 100, which we found is 16.25, means what? Well, we're producing 100 items. The average cost is going to be 16.25 hundredths of dollars, which means if I just multiply that by 100, then I get 16,250, and thus this means that the average cost of producing the first 100 items, we don't know what those items are, is $16,250 per item. Right? So I don't know what they're making. I don't know if they're making cars. I don't know if they're making elevators. I have no clue. But that's what it is. That's what it means, right? On average cost. Now, what about C prime of 100? That's where our derivative idea comes in play. C prime of 100 was 5, remember. And what that means is, again, keeping in mind that this output here is 5, right? Is that it means, based on what we wrote above, remember, right up here, remember that the marginal cost, C prime of X, is the approximate cost to produce one additional item after X items. So what does it mean? It means that the additional cost of producing one more item after the first 100 items is approximately, right? We're not claiming that it is actually equal to it, approximately $500. That's how we're using the derivative here, as we showed earlier. So as we can see, we can use the derivative to calculate things in other situations other than like the position function, which we focused on in the last video. And I do have a couple more problems here to look at in this video, just to get a little bit more variety. And so in the next example, we have a situation in which we're dealing with continuous compound interest. So it's kind of a finance situation here. If a principal, let's say P, is invested into an account, so think you got some money, you want to put it in an account, invest it, whatever that amount is. And that has an annual rate, R, so some percentage that you get on top of what you invested for, say, T years, and we compound it K times. So compounding means, right, is each time I compound it, we tag on that interest amount from the annual rate R. So maybe I get the interest once a month. Maybe I get it twice a month. Maybe I get it 3 times a year. I don't know. But we do it K times every year, that process. Then, as we let the number of compounding periods go to infinity, so I'm just, boom, I'm doing it, tagging on that interest every moment of time, continuously, as we say, then the amount of money that will be in the account after T years is given by this formula here. A is equal to P times the E R to the T. P-E to the RT, should I say. So that is our continuous compound interest formula, and hopefully you've seen it before. but just kind of reminding ourselves of this. And that's our continuous compound interest formula. So, we got an exponential function here with base e, and we could do stuff then. So let's just suppose that we invest $1,000 into some account. So that's like my P value there. And it's compounded continuously, meaning it's following the formula above. And we do this with an annual interest rate of 3.5%. Then the question is, how fast is the investment increasing after 20 years? So at that moment in time, 20 years since I invested this $1,000 at this rate, compounded continuously, how much more money am I getting per year, if you will? Well, that is just our derivative again. So first things first, let's set up A of t here. In general, if I let t vary with the principal amount of 1,000, then I would get the function A of t is 1,000 times e to the 0.035 times t, converting the percent to its decimal form. And thus, I can go ahead and differentiate this. A prime of t here is going to be 1,000 times 0.035 e to the 0.035 t, remembering our differentiation rules for powers of the natural exponential function. And of course, if you simplify that, that just simplifies to 35 e to the 0.035 t. Now, that is how much will be in the account after t years, assuming all of this is happening. And so what I'm after is how fast my investment is increasing, because it's definitely going to increase here. After 20 years, the rate at which that's happening. So that means I got to find A prime of t here. This gives the rate of change of the amount of money per year, right? Keeping in mind those units. Change in the amount of money per year in general. And so if I then take that function I just found, okay, right above, and I plug in my 20 into it, A prime of 20, then I'm going to get that thing that I'm looking for, which is 35 e to the 0.035 times 20. And if you press a few buttons here, you will find out that this is approximately $70.48, keeping in mind that this is a rate and it's really $70.48 per year, right? Change in output over change in input. So what that's telling us is that I invested $1,000 into an account that is compounded continuously at an annual rate of 3.5%. Then after 20 years, the amount of money that I should expect to get back the next year in my account should be $70.48. Right? So every year at that instant, that's how fast it's increasing. Now, maybe 30 years down the line, right, this will be a different number. It'll be a little bit more because we gain more and more each year. Another way to use a derivative, rate of change. All right, so we're going to take a look at one last example here in this video. And in this last example, what we're given is the temperature, call it big T. And let's say big T is measured in degrees Fahrenheit. And this temperature in degrees Fahrenheit is for some hot bowl of soup that's left on the kitchen counter. And it's given by the function y is big T of little t here, where little t is measured in minutes since the bowl of soup was put on the counter. So what do you got? You got a hot bowl of soup. Maybe it just got scooped it out of a pot from the stove, and you put it on a counter, and what's going to happen? The temperature is going to get cooler and cooler as time goes by, assuming, of course, you don't live, like, say, in a 200-degree house, which probably is not very feasible for most human beings. But assuming that's not the case, then the bowl of soup will cool, and the temperature at any given time, t minutes since it's been placed on the counter, is given by big T here in degrees Fahrenheit. And so as you can see on the screen, the first question is big T prime of little t here positive or negative? And this is just to conceptualize here. So based on what we just said, right, the temperature big T is going to be decreasing because it's hot at the beginning and then it cools down, gets close to the room temperature as time goes by. And so in this case, the answer is going to be, well, big T prime should be negative here, since T, the temperature itself, is decreasing. So we don't really know what the formula here is for this function, but whatever this function is, we know it's going to be decreasing. So the slopes of its tangent line anywhere at any given little t is going to be negative, and that's because the function big T is decreasing here. So big T prime going to be negative. And then the last question on this video for the same situation, let's say we're given the statement big T prime of 10 is equal to negative 1.5. What we're asked to do is explain the meaning of this statement in the context of the situation and make sure to include units. So, of course, that 10 there indicates that little t is 10 minutes, right? So basically 10 minutes has passed since we put the hot bowl of soup on the kitchen counter. And then the output there is negative 1.5. So the negative 1.5, we should note one thing about the outputs here for T prime, big T prime that is, that big T prime will have units of degrees Fahrenheit per minute, right? Because the change in the output direction is change in degrees temperature Fahrenheit, and the change in the input direction is change in minutes time. And thus, what this is really saying here is that, all right, this statement, big T prime of 10 is equal to negative 1.5, means that after 10 minutes of being on the counter, right, the soup that's in that bowl, of course, is decreasing, and decreasing here because the negative sign, right, the soup is decreasing in temperature at a rate of 1.5 degrees Fahrenheit per minute. So notice in that statement, because I wrote the word decreasing at a rate of 1.5 degrees Fahrenheit per minute, I didn't put the negative there because I already wrote that it's decreasing, right? So if I were to say it's decreasing at a negative rate, well, that means something different. So in the end, this statement means, again, after 10 minutes has passed since putting the bowl of soup on the counter, the soup temperature is decreasing at a rate, an instantaneous rate of 1.5 degrees Fahrenheit per minute at that instant in time. And so in this last example, of course, it's all about interpreting a situation in terms of derivatives as rates of change. So we've seen 3 different examples in this video. Of course, there are endless examples. Anytime some quantity is changing, we can talk about that quantity's derivative, and that's kind of the point of this video, is to get, you know, just a little bit more variety of situations that you can say, okay, we can really apply the derivative really in any case, right? And so that concludes this video. Upcoming in the next video, we are going to look at the infamous chain rule. So until then, it is Math and Beeps, and I'm out.